Ladies and gentlemen, welcome to this new webinar hosted by DataM. My name is Lander Arrupe and I'm a mechanical engineer. My main work areas at DataM are tooling investigations and Copra product trainings, both Copra RF, open and tubes, and Copra FEA RF. Of course, also customer support is part of my job. So during the last 6 years, I have been analyzing tooling in direct contact with the customers. So I know the difficulties of the roll forming process and especially the problems of understanding the behavior of the material at the machine itself, where the dirty environment and most of the times the poor accessibility gives only the possibility for the operators who have been working for at least 20, 30 years on the machine know where the problem could come from. So let's start looking at how Copra FEA can help us optimize our toolings. And of course, you can write your questions anytime at the chat area. And at the end of the presentation, I will try to answer these questions. So, before we start, I'm just gonna open our Copra RF area. So I already have a tooling here. It's just a U channel where we have some punches, some side rolls. So to be able to analyze this with FEA, we have to just two simple steps. We create a folder where everything will be saved. And the second step would be to set the parameters of the simulation. For example, if we really want the punches also meshed, so the strip will be with holes, some material specifications and process specification itself. If we want to also use friction for the simulation, cutting after the roll forming operation, and we just click at Run Project. Due to the fact that we have some holes, the machine takes a little bit longer, the creation of the FEA model. But once the model is created, we actually could run the simulation right away. So creating the FEA model is totally automatical, and the calculation itself could take long, yes, for sure. But we can leave that running, the simulation, and try to do other toolings. And once the simulation is done, now we see that our Copra FEA opened. The model is created. We can see the rolls. We see strip. The strip has the holes, which are also automatically created. It's not necessary to do manual modifications. And then, as I said, we could run the simulation, and once it's done, the tricky thing is to investigate these results and optimize it if it's necessary. So let's go back to the presentation. So the main topics we will be talking about or the main examples, I would say. It's these 5 examples we've been working. We have a lot of more, but these are the ones we can show also. It's a punch profile, air bended profile, a profile with difficulties for the flow inward movement and the consequences of this, a profile with spring back issues, and one of our 3D profiles in our research and development area. And at the end, just a couple of a picture of the new upcoming FEA, which will be released on summer this year with the new user interface, and with new function of remeshing, dynamic remeshing during the calculation that will make our life so again much easier. So Copra FEA is the best tool for experience building and know-how transfer for future generations. No more experience gone when operator goes in pension. But of course, as I said, will not substitute a good qualified operator. It will make him much better to understand things and to be able to reproduce also the good examples. Results, but we have to be aware that results of the simulation are as good as how good we can create the FEA model compared to the reality. At the end, of course, the main target is to save money and get better quality products. So let's start showing a typical example, which we always like to use as it illustrates all problems the tooling can have. The real profile shows here on the left side that damaged punch holes, which the upper and the bottom hole contour are not parallel. Yes. So the first step would be to know where these damages happen and quantify this. And the second, of course, would be to investigate the causes. And in this case, there were 2 reasons. The machine setting was not right. The flower was not created with Copra, and after we created the flower with Copra and we matched the rolls, we saw that the rolls setup was not right. And the second one, and the strategy, of course, was not also the best one. We see here on the bottom right side how the whole face it's not parallel. So the optimization was done. Of course, these optimizations are not suggested by the FEA. The FEA will not tell you the solution, but knowing the problems, of course, it's the first and main step to get to a solution. In this case, the bending sequence was changed to 1 bend forming strategy. In the original was a 2 bend strategy, and we could see that the 2 bend strategy could not be used due to the punches made impossible to get a nice material flow to the inside. Also, the calibration method, the bending calibration method of the inside radius was changed to the material so that the material did not slip outside due to these difficulties to flow to the inside. So, bending sequence, 1 bend form, and calibrations were changed. The second example showing air bending profile in which we can see that the long leg has a buckle, and so we can think that there is too much material which is getting somewhere from somewhere to this area, yes. And we could see that the problem was that the necking of this 180-degree bend make that the material flow to the inside, which was trapped between two bends. So in this case, also again, the calibration method was changed. We could see that the constant radius in this case made difficult to the material to go to the inside, was trapped, and with a constant length of neutral line, the material flow to the inside was better. Of course, due to the fact that we are bending multiple bends at the same time, it will always be difficult for the material to get to the inside, especially when we are forming outside more than in the inside. So in this case, we can see the optimization in the simulation. It was before the optimization and after. Still there is a little bit of buckle, but it's a much better profile, and it will be more stable, and we will probably will be under tolerances after this. This means that the new strategy, with this new strategy, a lot of tools, a lot of roles had to be remade or returned. So that means a lot of money we could save using the FEA. This third example, this is a profile from Sanco machines of Canada. We worked with them in a cooperation, and we can see clearly in the picture, circled white, a end flare of the beginning of the profile, that like a twist. So this was not acceptable for the customer. So the tooling and this could not be solved in the setup of the machine. So investigating the results, the difficulty of the material due to the long legs and the stiffness of the material to get to this inward movement with this multiple bend also strategy that created longitudinal elongations. So after the optimization, the inward movement of the material was optimized with the Copra function trapezoidal forming strategy to get a constant beginning, little bitter, and then constant flow of material, and again in this movement again a little bit slowly at the end. This bend strategy, trapezoidal bend strategy, make the material flow much better and softer, and we can see that there is no longitudinal elongation anymore. This difficulty for the material to get to the inside also is visible in the simulation because of the material thinning we get at the bends, and before changing this material flow, the bend steps not to a constant like 5 degree or 15 degree steps, but really letting Copra create the bend steps in issues were much lower, and at the end it made that the profile stability is much better after the cut-off also, and the end flare issues were minimized. This is also one of our favorite examples because this is clear how Copra could have saved a lot of money in tooling and machine setup time. We see on top the real part which came out of the machine, and the simulated part we see huge waviness issues which could be reproduced in the FEA, and after the optimization we see that also it's the representation of the reality with the simulation is almost one-to-one. In this case, we could see in the simulation that one of the main problems was the spring back between stations that made that the material was not formed plastically, so that the theoretical deformation was much less. We can see here the wished blue cross section in the station itself. No, excuse me, the other way. We can see the red one in the station, and blue one is after, where it springs up, and of course the next step station will have to do the work that the previous one has not done. That means extra work, extra longitudinal deformation, and that means bad quality of the quality of the end product. In this case, changing also the calibration method, changing the way we work. In this case, working with the smaller inside radius reduced the spring back because the lower ratio inside radius thickness material properties makes the spring back behavior get minimized. Of course, we will always have some spring back, but we can see the difference also in the right area, where blue and red are the same cross sections. In this case, not only changing the strategy could solve all the problems, but we had to play with also the diameter of the rolls and the angle steps and the work angles during the conformation. So we see, working with the parameter diameter angle, we see that FEA, we can with the FEA get the longitudinal strain at the edge, for example, in a diagram, and this diagram shows us that with different parameters we get different longitudinal elongations. So logically, with the biggest roll diameter of the smallest work, we get the smallest longitudinal elongation. In this case, with 160 at 20 degree, the 0.7% longitudinal elongation. So the Copra FEA will help us also develop brand new strategies, try out different things, and DataM, for example, is proud to show this kind of 3D profiles in which the cross section varies along the length, or it can vary also in the depth. So this is a real part where we have some warping about 3 millimeters. We can see in this area where the cross-section changes. And of course, we knew we were gonna get that because we simulated before. And in the simulation also we can see this kind of behavior. And the tricky thing, of course, is how we can get rid of these problems. But that's up to the know-how of the company itself. Yeah. But that's how the customers they can get step further and get to be the best drawer formers in the world. So these are some examples I wanted to show you, and all of them show that the FEA is the first step to get to a good quality profile with the lowest or with the least expenses to get these results. Now going to the new FEA, which is coming out this summer. You can see here clearly that the user interface will change completely. This old-fashioned mark-mented window, it has been reworked completely, and now it's like a Windows on ribbon way to work, a more up-to-date way to work. For me also it will be a little bit at the beginning difficult, or will need some time to get used to this, but I think this is the first step also for the future, and this will also be user-friendlier interface, and will make that the user will feel also more comfortable with working with the FEA. And at the end, I think we can tell that this version will have the function with the dynamic remesh. That means that the simulation time will be reduced, and the quality also of the simulated part also will be better, and not just that the simulation time will be reduced, but the necessary simulations also will be reduced, always because of the difficulties to match the bending areas from the theory to the what's happening? Right. So the problem, as we can see here, is that when we mesh the strip, the position of the bends in the flat strip is located on the theoretical position depending on the strip width calculation we have chosen creating this. But we can see here that the strategy itself of the forming will vary, will change the position of these bends, because, for example, there are the left strategy with two bend strategy with 8 stations. The thinning of the bends is much lower than with the 4 bend strategy, where we get a lot of more thinning necking in the bends. That means that the strip width is different. So it's not the mesh. When we mesh the flat strip, it's the position of these bends. It's not just about the strip width, but also the strategy itself will have dependency on these positions. But this now with the remesh will not be a problem, as we can see. We will see in this video. We see that on the top without remesh, on the bottom with remesh. So we are without remesh. We have to bend. We have to mesh the bends from the beginning, the flat strip, but we are not really sure about these positions. With the remesh, we don't need that anymore, and we always will match the bend positions. Will always match the position of the rolls. So this is the main. We see the differences really here, and the quality of the simulation also will be increased. Time gain and quality increased. Okay. Also here we see a round tube. We simulate it to round, and we remesh to get the round to shape simulation with the results, with the material properties from the tube, from the real tube itself. So we are not simulating to round with the bends also from the square, but we get this meshing at the end. And this added to the fact that with parallel functions we can reduce considerably the simulation times, and with new CPU technologies faster developed, we can get to the wished target that the simulations take much less time than they do now. So that would be the end for this short webinar about Copra FEA and the new version, which is coming on summer. Now you can all use the chat area of NetViewer to write your questions or discussion themes. Otherwise, I would thank you for your attention. Until next time then. Bye bye.